what is a magnetic field?
I don't know, bro.
Have a magnet. This is what a magnet looks like, as you probably know. It has a north pole and a south pole. And a magnetic field flows
Oh, for real?
from the north to the south. All these magnetic field lines are closed loops. And yeah, so this little magnet here, this is called a magnetic dipole, because similar to an electric dipole where we have a plus and a minus, I mean the field lines look the same, and it has like each side is opposite from each other. So magnets are actually constructed of tinier little magnets, which are called domains. So you can imagine each individual magnet here has a bunch of tiny little south and north magnets in them. And the alignment of these domains determines the alignment of the whole magnet in total. So if you have a bunch of scattered domains, as most objects do, it will just end up neutralizing and you pretty much have no magnet. So, the concept of a magnetic field seems clear, like we all know about magnets and that they just attract and repel, but you haven't probably really been explained yet exactly what a magnetic field is, and it's really an extension of electric fields. All electric and magnetic forces are in the same category of fundamental force, which is called the electromagnetism force. So it seems counterintuitive that electricity and magnetism are completely different concepts, but they're also the same concept. And the reason why is because a magnetic force is just relativistic effects of an electric field, electric force. So essentially, when you have charges that are moving, these charges experience apparent compression in their frame of reference, or the opposite of compression, which is, I don't even know. And they will have perpendicular forces, which are magnetic forces, or magnetic fields. So you don't need to know exactly how this works, but it's good to know that magnetic fields are just electric fields that are like moving pretty much. Yeah, so if you have two charges, for example, and they're moving in the same direction, they're going to somehow attract, just because of the way the shifting frame of reference has to account for the other frame of references because of the theory of relativity and stuff. So, yeah. Okay, so back to our magnetic dipole. We have a property of electric fields called electric flux, and similarly we have a property of magnetic fields called magnetic flux. So magnetic flux is equal to, as you can probably guess, this is flux B. By the way, B represents a magnetic field, and B is measured in Teslas. So magnetic flux is equal to the integral of B dot dA, just like the formula for electric flux, which is integral of E dot dA. And B is measured in Teslas. And then magnetic flux is measured in Webers. So all of these, because all of these magnetic field lines are always closed loops, because this dipole, a magnetic monopole doesn't exist, and there's always magnetic dipoles. That means that the magnetic flux of any closed region will always be 0. And you can think of that intuitively because if you have like a positive and a negative charge, if you just imagine that there are always positive and negative charges and they're always stuck together, then if you try to get some electric flux out of that, you enclose some region, use Gauss's law, you had Q enclosed over epsilon naught. This Q enclosed is just always going to be equal to 0. So you always have 0 if you had positive and negative charges always stuck together. And that's just the case for magnetic domains, because the domains, which are the fundamental like model we have for magnets, always contain one north and one south pole, and therefore can never enclose any like magnetic substance in them. So because of that property, magnetic field lines will always be closed, and for that reason, magnetic flux of a closed region will always be 0. So we had magnetic flux is equal to the integral of B dot dA. If we enclose that, then this would be equal to 0. Okay. In addition to the property of permittivity of free space, which you might remember, we have the permeability of free space, or the magnetic permeability of vacuum. Permeability, that's a hard word to spell.
Isn't that the coefficient of friction, actually?
Yeah, mu is also the coefficient of friction, but you know, it has multiple uses. So
Isn't epsilon also supposed to be like a
EMF.
I forgot.
Yeah, EMF. The relationship between
Permeativity of free space.
the relationship, which you do not have to know, between permeability and permittivity of free space is mu0 is equal to 2 times the fine structure constant, which is some random constant, divided by the square of the elementary charge of a particle, times Planck's constant over the speed of light. Great. No one cares. But this is the formal definition of magnetic permeability of free space. Oh, sorry, I missed the relationship between the two. Oh, right, okay. And also, mu0 times epsilon 0 is equal to the inverse of the square of the speed of light. So don't ask. Yeah. So that means that even though this formula seems really useless here, it does somewhat significantly mean that if you increase permittivity of free space, then you will decrease. I mean, if you increase the permittivity of an object and you decrease the permeability of an object, I mean, they're going to stay inversely proportional and stay multiplied to the same thing, unless somehow you manage to change the speed of light. So yeah. Okay. So then we have the difference between ferromagnets and paramagnet. God, I can't talk. Ferromagnets and paramagnets. So we just imagine a magnet as like a magnet, but some materials are ferromagnetic, which pretty much means they're permanent. Ferromagnets can be disturbed and rendered no longer ferromagnetic if the right conditions are met, but essentially their domains just stay in the same place. Paramagnetic is temporary.
It's like an electromagnet?
Not an electromagnet. A paramagnet is an object that, when touched with a magnet, can align its domains to act similarly like a magnet. It's like a magnetic capacitor in a way.
Oh.
It keeps a magnet when it touches a magnet. So this differentiation may seem confusing, but it actually happens all the time, and you might not realize it. If you have like a refrigerator magnet and you put it on your refrigerator, then it sticks. But if you take a piece of metal and you stick it on your refrigerator, even though that piece of metal may stick to the magnet, it doesn't stick to the refrigerator. Because like the refrigerator is like the receiver in that case. So here's an example.
The fridge is ferromagnetic.
The fridge would be paramagnetic.
Para.
Yeah, and the magnet would be ferromagnetic. So here's a magnet. This one sticks to the whiteboard. And then we have a paper clip and this little other piece of metal. And they don't have any attraction. I'm gonna get like a washer to make a little chain here. If we take the magnet and attach it to this little metal thing, boom, is that not just because it's this washer, they all stick together. If you take off the magnet, then the rest of them just fall off. Oh, or I guess it keeps its magnetism for a little bit until it like re-equalizes out. But yeah, these would not normally stick together. They just temporarily stick because it's magnetically aligned by the magnet. So then there's also an electromagnet. That's different than both of these types of magnets. Okay, finally, domains, which is the model for magnets, are just in reality spinning electrons. So electrons have an intrinsic property which we call spin, and it's kind of confusing because a point particle that is an electron can't exactly spin because it's a point and therefore doesn't really have a definition for spinning. But physics sort of shows that they do actually spin. Electrons will either have an upspin or a downspin, and that gives them a small little magnetic dipole field. So, but if you would imagine a bigger charge spinning, we'll get to the reason why in a minute. But the rotating of these electrons will have a magnetic field that comes out of the whiteboard. Again, we'll get to why in a minute. So moving electrons and rotating electrons both create magnetic fields. So domains are pretty much just spinning electrons or electrons that happen to be shaken around cause magnetic field in a stationary object. Okay. So, creating a magnetic field. I'm not sure if you guys are familiar with the right-hand rule, but we're going to start using it a lot during this lecture. So essentially, if we have a moving charge, we're just going to use a positive charge for now because it's simpler to do the math with, although electrons are commonly the charge that move. If it is moving upwards, we can use our right hand to represent the way that the magnetic field is going to curl around the moving electron. So if our thumb represents the velocity that oh man, my nail is dirty. Wow. If my thumb represents the velocity of the moving charge, then the way that my fingers are curling and pointing is the way that the magnetic field is going to be going around it. So we're going to have a magnetic field around this moving charge. Looks like this. Imagine this behind this. This is flat. This is a flat rotating thing. I should probably draw it more eccentric of an oval. It's like this. This velocity of a charge will create a field that way. Additionally, we're going to start using notation for directions that aren't in 2 dimensions because a lot of magnetism has to do with 3 dimensions. In the notation for that, on a whiteboard or a paper or a screen, an X and a dot. So the X represents going into the whiteboard, and the dot represents going out of the whiteboard. So you just have to remember that. So yeah, if we were to draw a electron moving this way, Nathan, can you draw on the whiteboard the magnetic field? Close. Because the charge direction, the negative charge is moving that direction, so the positive charge would be moving the opposite.
Oh wait, sorry, the X goes in, not out. Yes. The X is going into the whiteboard like this.
Yep.
Okay.
Yeah. So you,
Oh, we have to do this on an AP test?
Yeah.
This is a stupid way to...
You pointed your thumb away, like the direction opposite
Yeah, 'cause
the
it's
velocity,
negative.
because it's negative, correct. Alright, nice, so that's good. You could draw it like that and you could be like, oh, X, 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 da, 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 roughly. Okay. So that's the magnetic field created by a charge. If this charge has a velocity this way, then the magnetic field would be out of the screen here, into the screen here. And remember that's just because magnetic field is spin. Looks like this. And then you can also draw bigger ones. Because, you know, they go far away. Okay. So that is the magnetic field created by a charge. And then on the flip side, we have the magnetic field experienced by a charge. So with magnetic fields or magnetic forces, we typically have one charge that we call the experiencing charge and one that's called the creating charge of the field. So let's draw two charges. This charge creates a magnetic field that is out of the screen here and into the screen here. And then this one is going to experience this magnetic field. And because it is moving in a magnetic field, it's going to experience a force. So that is the magnetic force. So the formula for force of an experiencing charge, the first formula, the flux one, is force vector of experiencing is equal to Q, which is a scalar value, times V, which is the velocity vector, cross product the magnetic field vector. So this is when we're going to first start really using right-hand rule. So let's go over that for now, or for a second. The rule for right-hand rule is A cross B equals C vector. And then A is your pointer, B is your middle, C is your thumb. Of your right hand, don't use your left hand because then you'll get the opposite result. So if we have A pointing one direction, then we have B, which is our middle finger, pointing another direction. Our C value or direction would be the direction that our thumb points. So that will always work. And remember that if we have A and B, which are not necessarily perpendicular, like we could have our middle finger pointing down this way or pointing close to this, it doesn't affect the direction of our thumb. It will just decrease the value. Unless they're pointing completely parallel here, in which we'd have no value. So remember that absolute value of F is equal to absolute value of, or sorry, in general, absolute value of A cross the absolute value of B. Oh man, okay. Absolute value of A cross B is equal to AB cosine of theta. Or sorry, oh my god, sine of theta. Sine of theta, there you go. Alright, so applying our cross product into the formula for experiencing force.
Wait.
Okay, my bad. I'll leave that up. So which direction of force with this
By
charge.
absolute value, you mean the
experience.
magnitude?
Yeah, magnitude.
So would that be 2 absolute values or something?
Yeah, it doesn't really matter. It's the same thing. Roger, can you figure out which direction the force experienced by the right electron would be?
Okay, bro goes like this.
Yeah,
The
he's following
magnetic
it.
field would go like this. And so
Okay, careful. You're using your thumb for the magnetic field?
No.
Okay, you're using your middle finger?
Yeah.
Magnetic field is pointing in or out of the whiteboard?
Oh no, it'd be in. Cause like the guy, that guy would do that. Okay.
The dot is coming out of the whiteboard.
Oh geez.
What would V
Okay,
be?
so it's like that.
Yep.
Okay, and so it would be going out like that.
Okay, so you're saying
Which word V?
Before you out like that.
it would be going like this.
Yep.
What were V and B?
Alright. V is velocity, V is magnetic field. Careful, that's not actually right. Because Q, which is a scalar, is negative,
Oh,
the electron is a negative charge, it would be going the opposite way. So don't forget to multiply in the charge when using the right hand rule. Even when just trying to solve for the direction, you need to remember to put in the charge scalar, or at least the direction of the charge scalar. Yeah.
It's negative. Yes.
A good way to remember the dots and the X's, because it's kind of confusing, is if you imagine like an arrow from like a bow, like shooting an arrow. If you're looking at the arrow, it looks like a point. And if you're looking at the back of the arrow, it's like little like feathers on the back of the arrow, which is a cross. So you can imagine like an arrow representing the direction of the magnetic field. And by the way, these symbols are also used for electric field, but just occasionally. More commonly for magnetic. So real quick, if the electrons were moving in opposite directions, which way would the magnetic field go? I bet you can guess. Or the magnetic force.
Well, it would just flip over, so it'd go out.
It would flip over and go to the right. Yep. What about this one? What force would this one experience? You don't need to do right-handed rule again, because it's just
that way.
equal and opposite.
Oh, it'd go the other way.
What? That's genius, bro.
Oh,
no, velocity's this way. Okay.
This X and this dot, these are applying to the magnetic field created by this one. We need different ones for this one.
Yeah, it'd be
We'd
like
have
this.
to-
With
we'd
like,
have to
it's
redo this.
reverse. It's reverse because
So this would be-
Yeah, bro.
Whoop-oh. Hold on, zero, then X over here. Alright, cool. So then we have wires. From some formulas we established in some previous lecture, that you don't need to remember exactly how this is derived, but we're just changing the equation to get magnetic field experienced by a wire. We had charge times velocity, charge is a Q. Charge times velocity, this is not volts. Usually little v is used for velocity, then big V is used for voltage. Charge times velocity over length is equal to current. So that's not confusing at all, but yeah, if we want to change charges moving in a wire. Because a wire with moving charges is also going to experience a magnetic force in a magnetic field. So we had with magnetic fields like this. This is, by the way, the experiencing magnetic field of a wire, not the one that is creating. Because wires create magnetic fields with the right-hand rule, just like moving charges, based on the current of the wire. So we had F is equal to QV cross B, right, with all of our vectors. And because Q times V over length is equal to I, take this, and then, so let's move this length to the right side. Q times V equals IL. Look, we have QV and here we have IL. So we're going to change this formula into F experienced by a wire is equal to IL. And L is a vector here. You could sort of use I as a vector, but it doesn't really matter. IL cross B. is the formula for the magnetic force experienced by wire. You just have to remember this, not how to derive it. So if we had two wires, we could treat one as creating the magnetic field. It's a terrible mark. I don't like this color. So this would have a current moving this way, and then if this one had a current moving this way, Nathan, which way would the wires or the force on the right wire be?
It's L x B. So L's this way. Which way is
If it had a current moving up, wouldn't that be electrons moving up? So it'd be the other.
If it had a current moving up, it would be electrons moving down.
Oh man.
Yeah.
Doesn't even make sense. What?
This is going into the screen, into the whiteboard.
So left.
No, whoa. Yep, left. It would have a force left. Yeah, so wires with the same direction of current flow attract,
Alright, I'll be back.
and with different directions repel. Okay. That's the wrong song. Okay. So now for a little bit more complicated formula, which is sort of like the Coulomb's law of magnetism. What if we have a curly wire? So let's say we have a weird curly wire, and we're trying to solve for the magnetic field at a certain point. Essentially what we're going to do is integrate over this wire to determine the total magnetic field, because each little chunk of the wire is going to contribute a little bit of magnetic field over here, because each little chunk of the wire has moving electrons. So the formula, first we draw our length vector for each point on the wire. I'll use a different color marker. Little length vector, and that's dl, and you know that goes all across the wire. And then we also have a current value at that infinitesimal spot. And finally we have a direction vector to the point we're measuring. So if we draw a little dotted line here, that represents the direction. And we draw a little unit vector here, that's r hat, which is going to be the radius direction in between the wire and the magnetic field receiver, the little location that we're trying to measure the magnetic field at. So the formula for this entire situation is called Biot-Savart's law. I don't really know how to pronounce it, unfortunately. Biot-Savart law. And it states that dB vector, so an infinitesimal amount of the magnetic field, you have to add up all the little infinitesimal amounts of the magnetic field for each section of the wire to get the total magnetic field, is equal to the permeability times current of each location, and then times the infinitesimal length vector cross product with the radius unit vector, all divided by 4 pi r squared. So this is like sort of like the big overkill formula that you can use to derive a lot of magnetic field expressions. Yeah. It can also be used with moving charges if you rearrange it slightly, but whatever.
And so r hat is the
Right, so if you want to integrate both sides of that equation, you get b vector integral over the length of the wire of all that stuff. And then you can just take out usually permeability. Let me just get this. What, Raja?
So r hat is the direction of the r vector.
Yeah, it's the unit vector, so it
Yeah,
will have a
okay.
magnitude of 1.
So you could also make it so it's like r, the vector of r instead of the direction of r over r cubed. Would that work?
I guess so.
But I mean, r cubed would have to be absolute valued.
Well, it's already absolute valued. It's a magnitude.
Oh yeah.
Yeah, so sure.
Okay, yeah. I was just.
I don't know why you do that, but
I don't know. I was just mad thinking.
yeah. That's your favorite word.
Mad.
Mad. Okay, for wires of long straight lines, that formula has been pre-integrated for us. Watch out. Here's our wire, and we have a whole load of current flowing through it. And we want to measure the current at that point, at a single point. So obviously the integral is going to look something like this with all these little direction vectors adding up. And it's going to be like bigger than just a small amount here because we have all this added up, but it's going to like converge to a certain number as you keep going along the wire. It's not going to just keep adding magnetic field forever as it gets really far away. So the formula we have for that is called Ampere's law, which actually makes kind of a complicated assertion about what happens with a wire like this, but it's useful nonetheless. So imagine this is our wire and it has a current coming out of the whiteboard. So this is like the cross section of the wire. Looks like this. We don't see the rest of the wire. Similar to Gauss's law, we can draw what's called an Amperian loop around this this wire to figure out like the total magnetic field that it creates. So the vector field for the magnetic field is going to sort of look like this. It has higher magnetic fields as you get closer and lower as you get farther. And so these are all going to be moving sort of in a circle. That's the whole point of this thing. Okay, so it turns out my phone actually died while I was recording this lecture, which is unfortunate, so I have to re-record the second half of it. And yeah, so I was just at Ampere's law, which is explaining how much magnetic field curls around a wire that has a current in it. So right, we have an infinite wire here, or a relatively infinitely long wire coming out of the whiteboard here. It could be, you know, in reality, like curved a little bit or ends somewhere over here, but as long as it's relatively large compared to this amount of magnetic field we're measuring from around it, then this law is valid because we're just trying to approximate the current. But anyway, so for an infinitely long, relatively wire with a current in it, we have the formula for Ampere's law, which is integral of B dot dl is equal to mu ni. And this formula makes no sense when you look at it at first glance, but what it really means is this is the current I that's coming through the wire, obviously, and this N is always paired with the I because it's like the amount of wires that have current. So if we had, for example, multiple wires, we had a cluster of, I don't know, maybe 5 wires, and they each had some current I, then the total amount of charge flow, the total amount of current, would be the sum of all the wires, right? So we'd have sum of I N is equal to the sum of all 5 wires, and if they all have the same current, we just have 5I would be the total current. So that's why we have Ni, because if we have multiple wires with that same current, then we treat it as the total current. And that N will always accompany I in equations like this, but you can drop the N in scenarios where it doesn't really make sense. So anyway, we have Ni, which represents the total current, and then we have mu, which is the magnetic permeability of free space. And then finally, we have this big nasty integral on the left-hand side. So the thing about this integral is it's a closed loop integral, similar to what you saw in Gauss's law. But the fact that it's a closed loop doesn't represent we have a closed sphere this time. It represents we have a closed line contour. So this is a two-dimensional vector field that we're treating here because we're taking a cross section of this wire. So we're gonna have some closed loop, which we call L, around this magnetic field. And this integral represents each little dl unit vector and the magnetic field at that vector there. So essentially, the total of all these little cross products of dl and the magnetic field of that vector are going to add up to be this value on the right side of the equation here. So the thing about this is called an Ampere loop. Amperian loop, I guess. And we can draw it to accommodate whatever shape of magnetic field we're measuring. So, you know, if we have a circle here, that's the simplest Amperian loop, and that's the most commonly needed one. However, if we have like more complicated patterns of current, we might need to use a different shaped loop to easily calculate that. So, carrying out this process is similar to that of Gauss's law, where you construct a loop on one side, evaluate the integral, and then set it equal to the parameters on the other side, and then rearrange your equation in a way to solve for one of the values that you need. So for example here, let's just solve for the current coming out of a wire. Or sorry, let's just solve for the magnetic field of an infinitely long wire, a basic wire, right, using Ampere's law. So if we just have this purple loop here as our Amperian loop, you know, it's traveling this way. If we look at these magnetic field vectors here, I just showed 4 directions, but you know, if we had a magnetic field vector here, we point this way, here we point this way. The magnetic field is all curling around this wire, and they're therefore all aligned with the Amperian loop we have here. And that's why this circle loop is special, because it's aligned with the way that the magnetic field is curling. Okay, so I'm going to simplify this. So you can see that all of our magnetic field vectors, B, are pointing in the same direction as all the dl vectors. And that means that because this is a constant integral now, the radius of this loop is constant, and therefore, well, we haven't proved yet, but we're about to prove. So I guess this is a premise for the proof. But all of the B values are going to be constant. So that means we can just boil this integral down into BL is equal to mu and I. Right, because an integral is just a multiplication. So yeah, now we're trying to solve for B, and we're simply going to divide L from both sides of the equation, and L being the circumference of the circle with radius r is going to be 2 pi r. So we have the B magnetic field around a relatively infinitely long wire carrying a current is going to be equal to mu and I over 2 pi r. So next we have a solenoid. A solenoid is simply a spiraled wire, and as we know, wires create magnetic fields. So if we draw this current coming in and out of the spiraled wire, we'll see that a magnetic field will come through the center of it like this. Magnetic field B. So in each little bit of the current flowing through this spirally loop, the magnetic field will point this way instead of changing direction, which is the convenient reason why we have a solenoid this shape. This spiral is to create a magnetic field in one direction. And that's why this shape is also used for inductors and electromagnets. So yeah, a solenoid creates a magnetic field in one direction, and it will become more clear to investigate this constructive effect of magnetic field once we break it down into a cross-sectional diagram. So if we take a two-dimensional representation of this spirally 3D object, which it currently is, we'll see the cross-section of the wires coming on the top and bottom with their currents in and out of the screen. So here are the 5 loops, or I guess I have 4 loops drawn here on the bottom and the 5 loops on the top. And if we have current coming in up through this loop and it's going like this, then we're going to have it going into the screen on the top and out of the screen on the bottom. As the current is going this way, it's going into the screen and then it comes back down and around and it's going out of the screen. So if we look at the little magnetic fields that are curling around these wire loops, this on the bottom is out of the screen. We have a magnetic field going this way. And on top, it's going the opposite way. And now it's clear why we have this additive magnetic field coming through the center. And you may be thinking, well, look at the top. The top then has magnetic fields the opposite direction, right? And of course, a solenoid will have some amount of magnetic field coming out of the top and bottom, but I mean, obviously, okay, of course it has some coming out of the top and bottom because all magnetic fields have to create closed loops by definition of magnetic field, right? So any magnetic field being concentrated through this loop has to disperse and come back to the beginning at some way. But in an ideal solenoid, as you create, a more ideal solenoid, that effect will become more and more negligible. So ideal solenoid we have its length is much bigger than the diameter of the solenoid, and the diameter of the solenoid is much bigger than the diameter of the wire. So these are the constraints for an ideal solenoid. Obviously, they're not ideal, but just as a capacitor has to have very big plates, a solenoid has to be very long for us to leverage, the full approximative ability of the equations that we derive from it. Sorry, just to recap, as the solenoid gets very long, these magnetic field effects on the top and bottom, right, because this magnetic field is going to be uniform inside of it, created by this bottom is going to cancel out this top, and created by this top is going to cancel out this bottom. So just as like the charges on the capacitor plates cancel out the top and bottom, a similar effect sort of happens for the solenoid, and we have a very dispersed magnetic field connecting all around. All right. So let's draw our Amperian loop for our assumed constraints of an ideal solenoid to derive the magnetic field of an ideal solenoid. So let's say we draw a square, or I guess rectangular loop around these 3 wires on the top here. Yeah, so we're going to ignore these bottom wires and just take the top wires, and that works for the derivation. This derivation is a little bit oversimplified, but it is completely valid in the realm of AP Physics. physics, the electricity, magnetism. So we know our magnetic field inside of the solenoid is going this way, and let's treat our Amperian loop vector like it's going that way, and then everything else in this Amperian loop is now perpendicular to the magnetic field, right? So these wires up and down, or not wires, sorry, these segments up and down are not aligned with the magnetic field at all. And this segment on the top is not experiencing a magnetic field. So let's set up our sides of the integral. We have the integral of B dot dl, and we can change that to the sum of all of the four segments, sum of B dot L, and the only segment that matters here is the bottom one, and it's uniform, so we're just gonna have BL. We're gonna call L this length of the Gaussian loop, or the Amperian loop, and B is the magnetic field that we're searching for. So this is the left side of the equation, and we set the right side of the equation equal to mu and I. So I, again, is just a constant for the solenoid, how much current is being applied to the solenoid, and N actually does matter here because we have three wires through this Amperian loop. So we have N and we have L here, so our equation is going to boil down to BL equals mu and I. So we can vary this Amperian loop in size, right? So if we just did it a smaller length and we only had 2 wires piercing through it, or we had all 5, the amount being measured by the Amperian loop doesn't matter because we should be calculating the same magnetic field no matter what. So if we rearrange this equation for magnetic field, B is equal to mu n I over L, we see that we have this n over I. And this n over L. And this n over L, we name the turn density. So the turn density of a solenoid is the number of turns per unit length. And we call that N. Therefore, the magnetic field of an ideal solenoid inside of it is equal to mu little n I. B solenoid. And that's our equation. So if you had a length of a solenoid and you knew the amount of loops, you could just change that to mu big N I over L. But the turn density is like an inherent quality in a solenoid. And it also shows that it doesn't matter how big or long your solenoid is, if you just like make it longer and longer, you have the same magnetic field density at any point inside of your solenoid.